As a reminder, the usual disclaimer applies here. We're dealing with high voltages here. We're dealing with vacuum tubes which present a risk of implosion. All of these can be hazardous or lethal, so if you're doing any of this on your own, you're doing so entirely at your own risk. Oh no, not another Heathkit C-3 condenser checker recapping video, I hear you yell. I mean, there's a bazillion of those on the YouTube already, and I feel I've seen all of them. And typically it'll be someone well-intentioned who basically will replace the two 8 microfarad electrolytics, and maybe they'll replace that 2 microfarad monster condenser and then call it a day. And if they're really good, they'll think about removing the 0.05 death capacitor, and who knows, maybe a 3-wire. Anyway, I've seen all of that. We're going to do this a little differently, try to make it more entertaining. I'm going to go medieval on this one and do the maximalist over-the-top refurbishment and obviously tear down. So it'll be totally rebuilt from scratch, and hopefully you'll find this, well, at the very least entertaining, I hope. So I actually got this unit at an ARRL tag sale in Newington, Connecticut. The ARRL periodically runs, although infrequently, runs a tag sale whereby they get rid of old test equipment, as well as, of course, unwanted radios and stuff of that nature. But this spoke out to me from a shelf, and it had a tag with a very low number of single-digit dollars on it, so it was irresistible. And I did check it out, make sure all the knobs work. They seem to turn freely. Switch works, main control works. It all seemed to be there. So what's to complain about? I can't resist this. And the case and cosmetics are really in good condition. Normally, I would refinish the external case, but in this case, it's not necessary, as you'll see in a second. It really is in pristine condition, and the feet are still there even so. Hey, that's a bonus. And of course the front panel's in good shape and there's no rust inside. We'll zoom in a little bit on the inside here and take a quick look as it came. Yeah, the eye tube I disconnected earlier because I wanted to test it. Make sure it at least glowed and worked to some extent, because the iTube, well, is certainly worth more than single-digit dollars today. So I wanted to make sure at least that worked, and if it did, that meant I got many times my money back. But I want the thing to actually be the subject of this maximalist over-the-top rebuild. Power transformer, I checked. All of the windings showed continuity and proper resistance, the primary, and I think there's 2 secondaries, so that also is something that would have been somewhat on obtainium, and or not worth obtainium if it had been if any of the windings had been open. The transformer is in good shape. The I-tube, again, I did test on just to make sure it worked on one of my Heathkit T4 or IT12 signal tracers, which use the same, I think it's a 1629 tube. This one's made by RCA. So it still has a fair amount of life in it, enough that it's worth using. I will certainly not be replacing it. There's no need to. So there's plenty of green glowage, and the eye in the eye tube works. So again, that's a very good thing when you get something like this. Apart from that, we'll move along. The rectifier tube here, I think it's a 1626. It's an antique. It's actually a triode, a surplus World War II triode that Heathkit probably had a boatload of, and so in this case they're using it strictly as a rectifier. By connecting the grid to the plate, I believe, and so essentially it's a vacuum tube diode, and they're using it just as a rectifier, and it does the job. But you'll see what we're doing to it. The socket it's in is not terribly in great shape. It is making continuity. That black socket there, It's the kind of thing that you have to diddle. We'll see what we can do about that. But all the pins are good. The tube does light up if I put filament on it, voltage on it, so that's wonderful. Notice I did hack the line card off because I didn't want to have temptation. Here's that monster 2 microfarad cap. I actually tested it separately, and it worked as a capacitor, but as you'll see, nothing here will survive this teardown and complete rebuild. The switch has its little 22K resistors. Those let you select leakage voltage. We're gonna do something about those because I'll have tested those, and all of those will have drifted all over the place. So it's not like they all drifted equally, which is what you'd hope they did if they did. But no, they're all at slightly different resistances at this point, so they're all going to get replaced. So because this is a bare metal teardown, like any such thing, you'd want to take some still pictures of everything. And so this is just a little slideshow montage of details of pictures. There's the main selector switch, which is with its resistors. And the reason I'm taking these pictures is for further reference, because as you'll see or imagine, I will not be able to use the manual to rebuild this from scratch because of the way it's going to get rebuilt. Just trust me on this one. There's the death capacitor, by the way, above, and there's the 2 microfarad monster. So the pictures are there just to remind me, in case there's some ambiguity in the schematic, what might have been connected to what originally. And so that's why I'm sharing these here. So when I said bare metal, I really meant it. Here's the main subchassis, totally taken out, stripped, polished, and in the process of being rebuilt with new stuff, except for the transformer, which I kept. But a couple of things. There's a what looks like a fuse holder on the right there in the middle. That is new. More on that later as we go through the final build. And on the left, the 1626 triode gets a brand new socket, gold-plated ceramic, so it ain't ever gonna wobble again. And on the underside of that chassis, a lot of brand new terminal strips. I love terminal strips. I hate putting components on sockets and overloading them. So as you'll see a little bit later, and there again is the underside of the 1626 ceramic socket, as well as the underside of that fuse holder. Before I talk about the particular components I've chosen to replace in the C3, I want to acknowledge a source of guidance which I'm using to have chosen these, and that is an article entitled Notes on the Heathkit C-3 by Kenneth G. Gordon, Whiskey 7 Echo Kilo Bravo. It's a 13-point article. I'll put a link to a copy in the description. And Ken has quite a few good ideas regarding how to substitute parts in the C3 and optimize it. And so for the most part, that's the guidance I've chosen, and it's reflected in my choice of components here. So let's start with the resistors that I've chosen for this C3. We're going to be replacing all of the resistors in the C3, and you can see a good portion of the ones which I took out of the old C3 when I disassembled it. Here, these are all carbon composition. They were all, as you can see, from 10% tolerance, as you can see from the silver band, and pretty uniformly they were all wildly out of spec. Being significantly higher in resistance than their nominal values. So in any case, they basically all needed to be replaced. I've chosen to replace them essentially all with either metallized film or wire rounds, and we'll talk about a few of these. And I won't go through all of them because after all it's just resistors, but some of them are worth noting, and they follow pretty closely top to bottom
the C3 parts list from the manual. With the exception of the very top ones here, these are 100K. There are two 100Ks, and these are going to be put across the 40 microfarad power supply caps for increased stability. And this is one of the items that Ken, in his article, mentions is useful. Apart from that, they're then going from top to bottom. They match the parts list exactly. A couple of them that are of note. These 5 are the 22K resistors which form the divider chain to do voltage selection for the leakage test switch. And Ken does suggest putting in 1% 22K wire around 2 watts, and that's exactly what these are. So they'll be going in and hopefully provide more stability and predictability to the voltage selector switch. Apart from that, a couple of others, particularly the bottom 3 sets here are the 3 different, actually they're 5 resistors, but they're 3 different precision resistors, which in Heathkit parlance really meant 1%. Of course, now all of these resistors are 1% and pretty much spot on. But this is the new 90K one, and this is the old 90K one that I put next to it. Of particular note, and by the way, the reason I put these old ones not in the big pile of discards, although they might be discarded, was because they're notable in that these are the 3 precision resistors that Heathkit originally provided in the kit, and they're pretty much all spot on, and we'll take a look at one of them. I'm still debating whether to use one of these old ones that you'll see or not. I wanted to take a closer look at the original 70-year-old 2K resistor that came with the kit, because it's noteworthy. And if we close up, we see the first thing it says is WELW something. And then we'll just keep turning it and read what it says. After that, it says panclimactic, I believe. Then C13, here we go, 2 kilo ohm, 1% QA, and made in England. So who knew about the United Kingdom's precision resistor engineering? So it's time to take a look at this because it is noteworthy. And let's connect up the other side of it. And remember, this is a 1% tolerance resistor. And we're basically looking at not a 1% resistor, we're looking at something like a 0.2% resistor. So I thought that was notable for something that is a resistor that is 70 years old. As far as the capacitors go, and basically resistors and capacitors are the only 2 kinds of parts there are in the C3 to replace. Here are the old capacitors, of course, on the right, and they're modern replacements. Not much to say about the old capacitors, except that, to Heathkit's credit, none of them were shorted, none of them were open, so they were all capacitors. I didn't test them for leakage, but they probably all suffered to some extent, especially the 240 electrolytics here and the 2 microfarad monster here. So obviously all of these had to go. So this was, by the way, this twisted together thing was how Heathkit provided it, the 0.02 precision capacitor that was called for. It was 2 0.01s that were precise and just twisted together. That's being replaced, of course, by a single cap. Top to bottom, they match the parts list that you see. Starting at the top, this is the new 200 picofarad capacitor, what Heathkit called the 200 microfarad one, precision one. It's spot on. But interestingly enough, the reason I brought this one out separate from the pile of dead ones, which you no longer see, is this one is still spot on and could probably be used just as is. The only downside to using this newer one is that it's nearly invisible, so you probably would miss it if I don't call it out somewhere in the actual C3. Anyway, going down the list, we have the 0.01. This is the new 0.02 quote precision, which replaced those two twisted together ones. Then we have this 0.05. This was actually the death capacitor, which was connecting one side of the line to ground. It's 0.05, and you really didn't know which side of the line it was connecting to ground, or more specifically to the chassis. So this would connect either one of the two sides of your line to the chassis and would pass quite a lot of current. That since it was a two-wire non-polarized line cord, if this was on the hot side, when you plugged it in, it would actually pass quite a bit of AC to the chassis, which could give you quite a tingle. If this would ever short, if the equivalent would ever short, that's why it was called a death capacitor, because then you had a 50-50 chance of it putting full line voltage on your metal chassis. Anyway, this 0.05, I may actually not use it, because what I'll probably do is use these two, since I am putting in a grounded line cord. These are 0.01 safety capacitors. One of them will go between line and ground, another one between neutral and ground. And they are 0.01 because they basically will pass far less AC to the chassis, even though the chassis is grounded, so that's not an issue. Then I guess the purpose of all of this was to reduce or eliminate incoming RF interference. These weren't here to provide outgoing RF interference, since there was no RF anywhere within the C3. So that's probably what I'll do, is I won't use this guy. I will simply use these as line bypass capacitors on the 3-wire line cord. Then down here we have this 2 microfarad non-polarized replaces the giant monster one, and then here are the two. These are the two 8 microfarad electrolytics, modern replacements. So I just want to show you why I feel the need to replace this, which is the power factor control of the Heathkit C-3. So this is a potentiometer. It's an 800 ohm wire wound, and yeah, I don't know if you can hear it. You can sort of hear the wiper going on the wire. And it also has, so it's 800 ohm wire wound, and it also has a dual pole single throw on-off switch. Now, most pots which have some kind of on-off switch are simply single pole single throw, basically designed to turn the AC on and off. This one, I don't know what it was originally designed for, but it has 2 poles, so it has 2 separate single throw switches. And I left the resistors on just to remind me which are the relevant contacts, because normally these are connected like that in the C3, and then this is used to short out the resistors when you actually turn the pot, well, what would normally be on. But let's just take the resistors out of circuit for a moment, and the first thing we'll do is just measure, make sure it's an 800 ohm pot, which it is. 0.9K. Okay, it's a 900 ohm pot. Good enough. And you'll see why that's fine in a minute. And so if I put it in the center and then I move it, I can go all the way down to 0.3 ohms and all the way up to 860 ohms. So that's fine. So the pot section is working fine. By the way, excuse the knob. I just put a knob on to make it easier to click. This is just a random knob. It is not a Heathkit knob. Now, what the problem is, let me show you what happens when I go across the on-off contacts, which are these. So let's start on the first set of contacts here. And these, again, these resistors are totally out of circuit. In fact, this one is out of the world because it's gone. All right, so obviously the pot is switched off. As I said, the pot is switched off, and if I turn it on, I'm getting 100 ohms, 93 ohms, 81 ohms. I'm getting all sorts of things. In fact, at one point I was getting into the kiloohms. I should be getting 0 or 0.1 because this is supposed to be shorting completely. So here it's all over the place. And by diddling it, I can sort of make it move around. Not good. 100 ohms. It's all over the place. So it's simply supposed to be a switch. In the off position, it's OL, which is what you want. In the on position, it should be very close to 0. Like here it's 1.7K. Okay, that makes no sense. Let's look at the other position. And we'll actually clip onto the resistor lead since it's there. And again, when it's off, it's infinite, which is good. And when it's on, this section of the switch is acting weirdly as well. 300 ohms, 200 ohms, all over the place. And I've tried doing this and better, but inevitably comes back to act weirdly. So again, off, on. Okay, now we're down to 4 ohms, but again, very erratic. So, you know, obviously there's some sort of oxidation going on the contacts that form these two switches. Unfortunately, there's no obvious way in. This seems to be sort of swaged onto the body, crimp, crimp, crimp. And so if I were to remove this, in fact, there's 4 crimps, 1, 2, 3, big crimp. There's no way into the switch to get to the contacts. This is totally sealed. So is the pot, by the way, pretty much. So it's a well-made. The good news is it was well made in its day, but there's no way of cleaning it. And not that you would want to clean a wire wound section, but in this case, I would love to be able to clean the on-off contact section, but I can't. So this is going to be replaced. And the challenge is finding, first of all, an 800 ohm pot, or slightly larger if I have to, and especially one with 2 sets of single throw contacts, which I've never seen before, but we'll look and we'll find one. So after a lot of searching, I did find something I think is going to be a suitable potentiometer with a built-in switch. It's not quite 800 ohms. It's a 1 kilo ohm linear, and it's not dual pole single throw. It's dual pole double throw. And there's one other difference, but here it is. I'll put up the model number on the text here. So it is a 1K potentiometer linear, and it works perfectly well as that. Plus, it's a DP-DT, not a DP-ST switch, but that's okay because I only need to use 4 of the 6 contacts. The main difference, though, is that this is not a click-on like a volume control. This is the potentiometer, but the slide switch operates with pull on, pull push, and it moves the slide switch as you would expect of a slide switch mounted in the back here. But that's fine. I'll simply make a nice little label for the front of the capacitor, the C3 capacitor checker, and I think this will work just fine. Here's the main C3 selector switch cleaned up, and with some but not all of the wiring installed, because the wiring is going to significantly differ from how the manual originally had it built. But all the components that are supposed to be here are here, including these. These are the 22K 2-watt wire wound precision resistors, and then at the very end here, this normally would have been a 10K resistor, but it's now a precision 11K resistor because that's what the article I referenced earlier calls for. So at this point here, we're pretty much good to go and install this at least in the chassis. And yes, all of this flyover wiring does have clear insulation sleeves around it for a little bit of added safety. So let's take a tour of this now final overly maximally restored Heathkit C-3, and I'll show you everything I did to it or overdid to it, because again, if it's worth doing, it's worth overdoing. So this was just an exercise in over restoration, if you will. So as you can see here, the front panel is in very good shape. I'll talk more about some of the labels I added to the front panel in a minute, but I'll talk about this one now. This is just these are just little piece out shape. Well, main control full counterclockwise exclamation point, meaning if you're going to do leakage testing, you should make sure that this control is in the full counterclockwise position, because there is a design flaw in the original Heathkit circuit, whereby if you had this all the way here and you were putting 450 across a huge cap, which is fine, but you then do a leakage test, it would pass, and as soon as you discharge it, if you had significant energy, which you would in that capacitor, a large capacitor, you would then blow out this pot. So because of that, you want to keep that there. Anyway, that's just one of the front panel labels. I'll talk about the other ones later. Moving to the back, first and foremost, a proper grounded 3-wire line cord. That's hardly surprising. But let's go up here. We redid the I-tube socket. This, of course, is a gold-plated ceramic socket with a little bit of homemade insulator on nylon standoffs here just for safety. That works very well. And a little harness goes down to where it normally goes. By the way, you'll notice there is now a fuse holder. This is an AC fuse holder. You'll see this in more detail as we look at the underside of this. The power transformer hasn't changed at all. Here's our 1626, I believe, tube. This is the rectifier tube. Again, it's also in a gold-plated ceramic socket. It will never come loose. You can't diddle it. It's in there solid. Looking at the main selector switch, these are, we saw this earlier as a little subunit that I'd created, but here it is mounted in the panel. These are all the 22K resistors that form the divider chain. Again, these are, I believe, 2 wire wound 1%ers. And then this is an 11K resistor here at the end of the chain. And they go around and they get wired. Here's where the components which would have otherwise come flying off the actual contacts on the main selector switch and be going places like to ground and other places. I put these on a tag board. There are a couple of, here is where the precision resistors are, and the 2 capacitors. One is like the 200 puff, that's the tiny little capacitor that you see right here. That replaces that domino cap, which was still good, but again, this is all modernized. This is a 0.02, now it's 130 volts. This is non-polarized and what replaces the 2 0.01s that are twisted together. So all of these capacitors are, although not technically precision capacitors, they're far more precise than even the so-called precision ones that came with the kit. And then things like the 90K resistor and the 2K and 200K resistors, which I selected to be proper so that the accuracy would be maintained. So anyway, that's just a much cleaner, makes for a much cleaner wiring. And so that's really our original main pot. That's really all there is on the top part of the new restored C3. Looks a lot cleaner. And here's the underside. We'll rest the transformer on a couple of bench cookies here, just so the tube and nothing else gets smushed. So here's the underside of our maximally restored C3. Starting with the power entry, a lot has changed here. So again, this is a 3-wire line cord. Obviously ground is going over here. The hot side of the 3-wire line cord is going straight into the bottom terminal of the fuse holder, which pokes out the top end. And by the way, the reason I mounted the fuse holder to this chassis was because if I mounted it anywhere outside, anywhere on this back panel, I'd have to make an equivalent hole in the case, and I didn't want to do that. And this fuse is not going to blow. So, so this is the AC line fuse. The output of the AC line fuse goes to a typical CL90 NTC, which basically acts as an inrush current limiter just for good measure. And then it goes to the main power switch, which is on the selector, and then back from the power switch, it goes to one side of the primary of the transformer, and the other side of the primary of the transformer goes to the neutral, as you'd expect. The 0.05 death capacitor, which was in the original Heathkit design, obviously I removed. And it truly was a death capacitor because, again, the original C3s had a 2-wire line cord which was non-polarized. And the 0.05 cap to the chassis, not to ground because, again, it's a 2-wire line cord, the 0.05 to chassis, you didn't know whether it would be on the hot side or the neutral side. So if it was on the hot side, basically the only thing between the chassis and the hot side of your life was that death capacitor, and if that leaked excessively or shorted, your chassis would now be at line voltage. Anyway, that's why they call it a death capacitor. As an homage to the death capacitor, I put two proper 0.01 Y rated safety caps between hot and ground now, and neutral and ground. So that's basically the entire power entry of this thing. Here we have the wires coming from the I tube, which go to their terminal strip. So as you'll see, I've added significantly more terminal strips because I do not like overloading controls and sockets with components. I put components on terminal strips or tag strips, not on tube sockets or pots or the such. So here here's where I put the capacitors on this side. These are the two 8 microfarad electrolytics, which are the main filter caps. They have these resistors across them. Per the original article I mentioned, apart from being bleeder resistors, these add to the stability of the DC power supply once it's rectified. Here, the only other two caps, here's a 2 microfarad non-polarized, which replaces that 2 microfarad non-polarized monster cap, which you would have seen in the original. It's rated at 250 volts, which is more than enough. And then a 0.01 here at 630. And again, these are nicely mounted between 2 parallel terminal strips. Moving along, things get even more interesting because here we have our rectifier tube socket. Nothing exciting there, except because I could, and because, again, if it's worth doing, it's worth overdoing, I decided to not necessarily use the rectifier tube, but use a full wave solid state bridge. And so I wired this solid state bridge rectifier, and it's rated to 630 or 650 volts or something, in place of the rectifier tube. But I didn't stop there because I wanted to be able to switch between using the solid state rectifier or the the full wave solid rectifier or the half wave rectifier tube. And to do that, I added 2 slide switches here, which are DPDTs. I could have made it 1 3-pole double throw, but I didn't have one of those, so I made it 2. This switch here turns the filament of the rectifier tube on and off. So this simply interrupts the filament. In case I'm not using the tube, I can switch it off, so there's no reason for it to consume power. And then this is wired such as to either switch in the full-wave bridge or switch in the half-wave tube rectifier. And so if I want to use, right now it's set to use the tube. If I wanted to use only the bridge, I would flip this and this. That turns off the tube and puts the solid state in the circuit. So I thought that would be an interesting way of adding excessive componentry to a restoration. But that's basically it for this overly restored C3. Proper binding post covers, and you'll notice the last of the extra terminal strips. These are the components which are typically before that ran off of the power factor control. The power factor control has been replaced, as you saw earlier. I had to replace it with this. It was an 800 ohm pot with a dual pole single throw switch. Here is a 1K pot with a push-pull DP/DT switch, which is properly shorting and switching the resistors here. And because it's no longer a turn to click, it's now a push-pull to click. Let's remove the bench cookies and turn this around again. And we see here that now our power factor switch, instead of being click to turn, it's now push-pull. And to remind me which is which, I just added a P-touch label. So if it's pushed in, it's designed to be used with electrolytics during the measurement of the top two scales, and I can adjust for the lowest or the most correct power factor that gives me the highest eye opening, which in my case is typically all the way at the bottom, because I usually don't have a lot of ESR on brand new caps. Or if for other capacitors, non-electrolytic, you simply pull it. You can push, pull, and that basically did the same thing as shorting the resistors in the original circuit. So that is our maximally restored C3. I thought I'd show you on the schematic the very, very few modifications I made, which are very few electrically. Obviously, I replaced all the electronic components, which is basically the caps and the resistors. The only values that ever changed are this 10K became 11K per the suggestions in the article I mentioned. This 800K pot, which is the power factor control, this 800K became a 1K. These were linear because that's what's available. And then over here, this is a little slide. This is the little slide switch that interrupts the filament voltage to the rectifier diode tube, which is here. And so rather than show the other switches wiring, which switches the full wave bridge in and out and modifies things, I thought I'd modify it with what I'll call 3D CAD. So this is the way it is from the factory, or wired when the other slide switch is in the tube rectifier position. And then here's what the schematic looks like when it's in the solid state full wave bridge rectifier position. So it's basically what you'd expect for a solid state bridge baked into this, put into this circuit. So I didn't show the slide switch. I didn't show all the slide switch wiring because I thought that would be more confusing than just this, which is really straightforward. And that's it. As it turns out, there are two versions of the schematic for the Heathkit C3 out there. There's this one, which we've been tooling with, and was sort of my reference one. But then there's also a different manual, and I think it's an older version of the C3 manual, which shows this one. Electrically, they're the same. This one is arranged more to sort of emphasize the fact that this is a bridge circuit of some kind. Now, how do I know that this schematic and this schematic are electrically identical? Well, because as you can imagine, when I rebuilt this C3 wire by wire with brand new parts and in the way I did over the top, I didn't use the manual step by step. I simply went by the schematic, but I took the time for every connection every wire and every component that I installed and connected. I simply highlighted it to make sure that I wouldn't miss anything, and I took the time to do it on both versions of the manual and so of the schematic, and that's how I know that both these versions of the schematic are electrically identical. I'm not sure which I like better. There's something to be said for the one that looks like a bridge circuit. On the other hand, I think the separating of the rotary switch into 3 wafers here, as opposed to combining 2 of the wafers into one, is probably a little bit clearer, but what the heck. So there you have it. But of course, there's more. The original Heathkit C-3 kit came with parts which would have you build a pair of test leads, so you could basically connect components to the unit without actually having to screw them onto the binding posts. So in that vein, I went ahead and created some beautiful little silicone, nice flexible, gold-plated banana plug Crocs with enough heat shrink insulation to basically allow me to clip them without touching the conductive parts. So these are kind of nice, and of course they would simply plug into here. And then the reason they're short is because this is not intended to be used in circuit. This is simply intended to be used to measure discrete components, of which there was one extra resistor provided with the kit, which was a precision 220K resistor. Here we go, and this is the one I'm providing with it. And the reason for this was to calibrate the instrument. Basically what you would do is you would connect it up to the unit like this, and basically then you would put the range switch into the R times 100 position, and then you ideally, since you knew this was 220K exactly, you'd want to position this until you got a full eye opening, like it is here, and then you would move the actual knob on the shaft with the set screw so it points straight up to the 2000 mark, because that's not coincidentally, that's exactly half range of the potentiometer to balance the bridge. So that's, you calibrate it simply by moving the pointer physically so it would agree with 2000 here. And you can see the full eye opening there. It's pretty much spot on. But of course, I go a little bit further. I provide a full set of components with it, which is basically one of each resistor. Well, in this case, the only other one I give you is a 2K, so you can have a look at the R times 1 position, or just R position. Basically, all the components necessary, one of each component, so that you can prove out each scale of the resistance and capacitor measurements. So there's a big old 47 microfarad electrolytic, and maybe we'll just look at that one. Of course, to use that, we have to move our banana plug to here, and we connect up the lead negative to negative, positive to positive. So our 47 at 450 here is still hooked up nicely. I'm going to put it down so I don't need to touch it during any of these tests. And I've dialed down the exposure a bit so the camera picks up the eye tube a little bit better. And so we can start, we're going to do 3 things. We're going to measure it, we're going to measure its CSR, and we're also going to do the leakage test, which are the 3 things that this thing can do to capacitors. To measure it, again, we've dialed up the range, which is 20 to 1000 microfarads over here. That's the highest range it'll measure. And then we simply turn the main dial until we see the eye open, and there it is, and we get maximum eye opening, something in this case shy of about 45. So that's certainly within the ballpark. And again, this, I'm touching it, this is not a precision electrolytic. I'm not sure there is such a thing as a precision electrolytic. But anyway, here's a maximum eye opening. To check the ESR, the manual basically says to turn the power factor switch and the combination of the main dial to the position which gives you the maximal eye opening. And so the maximal eye opening is here. And then as we notice, as we dial the power factor switch, that also affects the eye opening. But the maximal eye opening is when the power factor control is pretty much at the 0 mark. And that simply says that there's very little ESR as a percentage of, I guess, how much ESR there could be. If I dial this up, the eye closes, which means no, we don't have this much equivalent series resistance. So essentially, there's very little ESR. So the so-called power factor control does work and gives you, I guess, an indication of relative ESR as it is. Finally, of course, there's the all fun leakage test. So for that, we put the ESR all the way to 0. We take care to move the main dial all the way counterclockwise, because this is a case where we could damage its pot because of what I mentioned earlier. And we'll start at 25 volts, and eye is open, turn to leakage, charges up but opens up again, so certainly no leakage at 25. I'll spare you, I'll just go up a few voltage ranges. Since this does go up to 450, I'm not worried. I can go all the way to 450 here, or well, and hold it open, and now there's something around 400 volts across the thing, and the eye opens, so no leakage there. And as I release this, it's going to discharge the cap through an internal resistor and not through the main dial potentiometer. And so that, in a nutshell, is how it measures electrolytics.